Last summer, astronomers noticed something off, and it was, wait, that's not supposed to happen off. They spotted a weird mix of signals in their data. After double-checking, triple-checking, and probably staring at the screen in silence for a while, they realized it was something they'd never seen before. They may have just caught the first ever superkilonova. You've probably heard of supernovae, those big dramatic explosions marking the end of a star's life. It happens like this. A massive star runs out of fuel, its core collapses, and it blows itself apart. Sometimes a white dwarf star steals too much material from a nearby companion using its super powerful gravity. That stolen gas, mostly hydrogen, spins around the white dwarf in a disk and then slowly falls onto its surface, eventually triggering a massive thermonuclear blast. By the way, since we've mentioned it, a white dwarf is the scorching hot, ultra-dense core that remains after a small or medium-sized star, like our Sun, exhausts its nuclear fuel and blows off its outer layers to form a planetary nebula. Then, over billions of years, it slowly cools and becomes a theoretical black dwarf. It's roughly the size of Earth but packs around the Sun's mass, which makes it incredibly dense. Black dwarfs are powered only by leftover heat, not ongoing fusion. Either way, the birth of a supernova is loud and bright. These explosions often leave behind a neutron star, which is so dense that a single teaspoon of it would weigh about 1 billion tons. Basically, less star and more cosmic anvil. But then there's this rarer kind of VIP event, the kilonova. Astronomers have only ever seen one of those. Back in 2017, one event confirmed what scientists had predicted for decades. Two neutron stars slammed into each other and shook space-time with gravitational waves. Such collisions don't just look cool, they create heavy elements like gold and platinum. Kinda like a cosmic factory. There's a chance that the gold in your phone or on your finger was forged in a violent neutron star crash billions of years ago. Kilonovae have a signature look. The explosion produces so many heavy metals that they block blue light, leaving behind a deep red glow. It's subtle and incredibly hard to catch. Now, here's where things get interesting. What astronomers spotted in 2025 didn't really fit into the supernova box, but it didn't look like a regular kilonova either. It was too powerful and too strange. Neither did it behave the way either event should on its own. That's why some scientists believe they might have spotted something new, a superkilonova. We're talking about a collision or chain reaction so extreme that it goes beyond anything we've observed before. Right now, it's too early to draw conclusions. Astronomers are arguing politely, running more simulations, and waiting to see if the universe decides to do it again. Because in the universe, twice is often the proof. But how could this superkilonova occur? Scientists suggest quite a wild sequence of events. Picture this. A massive star collapses in a supernova, but instead of leaving behind one neutron star, it produces two. Almost immediately, those two ultra-dense remnants begin spiraling toward each other. Within moments, they collide and merge, setting off a kilonova on top of the original explosion. In other words, it could be not just one cosmic blast, but a chain reaction. Two of the most extreme events in the universe happening nearly back to back. The mystery itself started on August 18, 2025, when the LIGO and Virgo gravitational wave detectors picked up a signal from 1.3 billion light-years away. The event immediately caught attention. The ripples in space-time looked exactly like what astronomers would expect from two neutron stars crashing into each other. But there was a plot twist. The International LIGO Virgo CAGRA team quickly alerted astronomers worldwide. The data suggested a neutron star merger, but at least one of the objects seemed unusually small. Together, the pair weighed just 0.87 times the mass of the Sun. But neutron stars aren't supposed to be that light. According to everything we know, they should weigh at least 1.2 solar masses. At the same time, the analysis showed a 99% chance that one of the neutron stars fell below that limit. That shouldn't happen under normal conditions. So either the models were missing something, or this object formed in a completely different way. For example, it could be some kind of exotic birth during the collapse of a rapidly spinning, neutron-rich star. So, just a few hours after the alert, the Zwicky Transient Facility at Palomar Observatory spotted something curious. There was a fast-fading red glow coming from the same patch of sky. At first, it seemed that this discovery could solve the puzzle. For the first 3 days, the object behaved exactly like a kilonova. It glowed deep red, which is a sign of freshly forged heavy elements like gold and platinum. Everything matched: the timing, the color, and the gravitational waves. Astronomers thought they were witnessing the second confirmed kilonova ever seen. And that's where things got weird. On day 4, instead of fading away like a kilonova should, the object started getting brighter and bluer. That's like a major red flag in astronomy. Follow-up observations from the Keck Observatory in Hawaii revealed signatures of hydrogen and helium in the light, and those chemical fingerprints do not belong to kilonovae. They belong to supernovae, more specifically, a Type 2b stripped envelope supernova. This kind of explosion happens when a massive star loses most, but not all, of its hydrogen before blowing itself apart. It often happens because a nearby companion star siphons material away. At that point, many astronomers wrote the event off as a normal supernova that just accidentally happened near the gravitational wave signal. After all, regular supernovae don't usually produce detectable gravitational waves, but the timing and the early kilonova-like behavior, plus the strange mass measurements, didn't fit into that explanation. The event started to look like something far stranger. Now, most researchers still admit there's a chance all of this was just bad cosmic timing. Statistically speaking, they can't fully rule out that the neutron-star merger and the explosion just happened to occur near each other by coincidence. Still, the overlap in both time and location looked strange, and they couldn't ignore it. What if both signals came from the same catastrophic event? It would be an extreme scenario involving a rapidly spinning massive star. This star wouldn't collapse into a single dense core. Instead, its breakneck spin would cause the core to split in two, forming a pair of tiny underweight neutron stars. These newborn neutron stars wouldn't last long. Almost right after birth, they would spiral toward each other and collide. That crash would send out gravitational waves and create heavy elements, just like a normal kilonova. But all of this would happen inside a much larger supernova explosion. In other words, it would be a hybrid. One cosmic disaster stacked on top of another. Interestingly, the term superkilonova wasn't actually invented for this discovery. Originally, it described a theoretical event where a massive, fast-spinning star collapses straight into a black hole, surrounded by a huge disk of material. This material is capable of producing giant amounts of heavy elements, possibly several times the mass of the Sun in gold and platinum. The new study suggests using superkilonova to describe a supernova that briefly creates and destroys a pair of neutron stars before anyone notices what really happened. The team is careful not to oversell the idea. After all, the event happened far away. Moreover, the signals overlap in complicated ways, and untangling them perfectly isn't possible with current data. So, coincidence is still on the table. But if superkilonovae turn out to be real, they would help us solve several mysteries at once. For example, they offer a way to form low-mass neutron stars and help explain how the universe's heaviest elements might be created. Future observatories could help us figure out this phenomenon. Upcoming missions like NASA's Nancy Grace Roman Space Telescope and the UVEX satellite will watch the sky, increasing the chances of catching more of these blended explosions. If astronomers start detecting more mergers involving unusually small neutron stars, the case will finally be solved. Until then, the idea of a supernova and a kilonova happening together remains one of the most intriguing what-ifs in modern astronomy.
Oh man, the sun did it again! It just blasted a huge cloud of plasma into space. This time, it was one of the fastest and most powerful eruptions of this solar cycle. It was so strong that the shockwave hit Venus, our next-door neighbor. That's when scientists got worried and started asking a scary question. Could Earth be next? Well, let's just cut to the chase. If your GPS and internet have been working fine over the last few weeks, and your city hasn't had any big blackouts lately, you already know the answer. No, that powerful blast didn't hit Earth. Or at least we didn't feel any real effects from it, because this event happened in October 21, 2025, and if our planet had been in its path, we would have felt the effects only a few days after that date. You see, we're talking about coronal mass ejections, or CMEs. From time to time, the Sun throws a giant cloud of superhot plasma into space, straight from its outer layer, the corona. Think of plasma as a superheated gas. It's what the Sun is made of, and it's full of tiny charged particles, positive ions and negative electrons. These outbursts happen because the Sun's magnetic field is always moving and twisting. Sometimes the magnetic lines get tangled up, then suddenly snap and reset. This process is known as a magnetic reconnection. And when that happens, boom, the Sun launches a CME. A single coronal mass ejection can throw billions of tons of material into the solar system in one shot. And it can create a shockwave. That shockwave can speed up charged particles, which raises the chance of a radiation storm. And if a planet is in the way, yeah, that can be trouble. The tricky part is that CMEs are pretty unpredictable. They can blast out in different directions, and they don't all move at the same speed. The fastest ones race through space at millions of miles per hour. If one is aimed at Earth, it can get here in as little as 15 hours. Slowest ones can take days to get here, but even then, it's usually somewhere between 1 and 5 days. It's not like months. Since this big blast happened a while ago, it's safe to say that, well, we're safe. And honestly, even if it had hit Earth, we'd probably be safe anyway. Sure, a strong CME can mess with satellites, disrupt radio and internet signals, and even knock out power grids for a while. But it's not the kind of thing that ends the world or wipes out humanity. So take a breath. Even a really powerful solar eruption isn't going to destroy Earth. Unfortunately, we can't say the same thing about Venus. CMEs hitting our neighboring planet are actually one of the reasons Venus can't support life, at least not what we consider life. But don't worry, we'll get to that part later. First, let's dive into this recent solar outburst and what made it so extreme. This one came from the far side of the Sun, the side we can't see from Earth, and it came from an especially active sunspot area called 4246. This is a new, huge, messy sunspot that's been responsible for the latest round of solar storms headed our way. The big blast happened right after that region rotated past the Sun's western edge, so it was out of view from Earth and from most weather satellites. Thankfully, the event was caught by an instrument on a NOAA satellite called CCOR-1. Think of it like a special camera designed to spot big solar blasts even when they happen on the far side of the Sun. That's why it's strategically placed so high above Earth, and it orbits about 22,000 miles over the equator. The CCOR-1 manages to capture those images by blocking the Sun's blinding surface, so it can see the faint glow around it and track huge plasma clouds as they spread out into space. Now, let's talk about speed. NASA estimates that the CME in October was moving at about 820 miles per second. But the first radio signal suggested it might have been even faster, close to 1,537 miles per second. Trust me, that's crazy fast for a coronal mass ejection. To put that in perspective, only a handful of blasts in modern history have been quicker. One famous example happened in 2017 during an X-class flare rated around X8. So according to NASA, X-class means the strongest kind of solar flare. The number tells you how strong it is. An X1 is the baseline, an X2 is twice as strong, an X3 is 3 times as strong, and so on. So yeah, an X8 flare is something huge. Back on Earth, that 2017 event did mess a bit with high-frequency radio signals for a while. But for us, that was pretty much it. Mars was a different story. When the same event hit the red planet, it heated the upper atmosphere in an uneven way. In the hottest areas, scientists saw the top 2 layers, the thermosphere and the ionosphere, start interacting more than usual because of the blast. And that had a real effect. Oxygen began escaping into space much faster than normal. In other words, that brief event made Mars lose part of its atmosphere at a higher rate. Now, when we talk about this recent burst, the story is kind of similar, but with a twist. This time, Mars wasn't the main target, Venus was. The planet was sitting right in the path of the solar burst. So when the blast hit, Venus got slammed with a storm of charged particles. Now you might be wondering, why is it a bigger problem when a solar eruption hits planets like Venus or Mars, but not as big of a deal for us here on Earth? Well, it's because of Earth's magnetic field. So big blasts from the sun can mess with the atmosphere around a planet. But on Earth, a lot of that impact gets blocked by a natural magnetic bubble called the magnetosphere. Good thing, huh? Here's how it works. A wave of plasma comes from the sun and slams into the magnetosphere, the region around Earth controlled by our magnetic field. That magnetic field pushes most of the charged particles away, kind of like a shield, but not all of them. Some particles still sneak through and crash into the upper atmosphere. When that happens, we can get geomagnetic storms. These storms create amazing auroras. They can also mess with satellites and communication networks, like we talked about earlier. But some planets, like Venus, don't have a strong magnetic field like Earth does, and that can be bad news. Because when a CME wave reaches Venus, the charged particles crash straight into the atmosphere and, over time, slowly peel parts of it away. Now here's a real example. On December 19, 2006, the Sun released a small, slow CME. Even though it wasn't moving fast, it was still strong enough to do damage. About 4 days later, it reached Venus and ripped away a large amount of oxygen from the planet's atmosphere, sending it off into space for good. Or bad. And this is actually one of the big reasons why planets like Venus are uninhabitable. Without a strong magnetic field, CMAs can slowly strip away their atmosphere, blast the surface with dangerous radiation, and create brutal space weather conditions. Venus is a perfect example. It is the hottest planet in our solar system, being 100 times hotter than Earth. Its atmosphere is insanely thick, and the pressure over there is insane, so much so that the longest any spacecraft has survived on its surface before being crushed is a little over 2 hours. Scientists think that getting hit by solar eruptions without a proper magnetosphere to protect it helped push Venus toward this extreme world. And by studying what happens to planets like Venus, we can learn something bigger: how important a magnetic shield might be for life on other worlds we find outside our solar system. The protective shield of our planet decays and eventually fails. So do our satellites. First, communication satellites in the highest orbits go down. Next, astronauts in low Earth orbit can no longer contact their mission control center. And finally, hazardous, relentless cosmic rays start bombarding everything on Earth, causing havoc and devastation. Are these the terrifying consequences of the planet's magnetic field reversal we're going to face? Right now, as you're watching this video, Earth's north magnetic pole is extremely out of whack. It's so serious that scientists will have to update the global magnetic field model released a mere 4 years ago. Does it all mean that the magnetic pole of our planet will flip soon? Well, be patient, we'll figure it out a bit later. You see, the magnetic pole is moving quite erratically from the Canadian Arctic towards Siberia, and these movements are very unpredictable. But it's normal for the pole to be moving. There are long-term records from London and Paris that prove that the North Magnetic Pole moves randomly around the rotational North Pole over periods of several hundred years. But the most astonishing thing about its movement is that it's speeding up. Around the mid-1990s, the magnetic pole unexpectedly accelerated from a bit over 9 miles to 34 miles a year. And recently, the pole crossed the international date line, moving toward the eastern hemisphere. The European Space Agency launched extremely accurate magnetic field satellites in 2013. Thanks to them, researchers have superb data they can use not only to make magnetic field maps, but also to update them every 6 to 12 months. That's how they were able to notice that the core field was weakening too. It might be a sign that the planet's magnetic field is about to flip. To understand this process better, we need to figure out how the core field works. Let's say we've got a bar magnet that runs through the center of our planet and has a north and a south pole. This magnet is incredibly strong, representing about 75% of the intensity of our planet's magnetic field at the surface. Our bar magnet is not only moving, but is also getting weaker, by about 7% every century. Admittedly, this bar isn't the perfect representation of the core field. It's more like electric currents generating Earth's magnetic field. Still, this model makes it easier to see what's happening to our planet now. The magnetic field of our planet plays an important role in protecting us from dangerous radiation and geomagnetic activity, which is the product of the interaction between the solar wind and Earth's magnetosphere. Earth's magnetic field also moves. Scientists have been studying and tracking the movement of the magnetic poles for hundreds of years. The historical motions of these poles indicates changes in the global geometry of the magnetic field of our planet, and they may point to the beginning of the field reversal too. That's what the flip between the north and south magnetic poles is sometimes called. You see, if the north magnetic pole moves a bit, it isn't a big deal. But a complete reversal might have a serious impact on the climate of our planet, as well as modern technology. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. So those scary events from the beginning of the video aren't likely to happen to us. The magnetosphere will continue protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges called electrons moving through the metal. The current is what generates a magnetic field. Earth has a liquid iron core. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving through the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic radiation, which otherwise would be extremely dangerous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons and capable of reflecting radio waves. The interaction between these two layers and the magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. But sometimes, the sun starts shedding gargantuan magnetized clouds of gas that can accelerate to incredible speeds. They're called coronal mass ejections, or CMEs. They're ejected from the sun over the course of several hours. CMEs usually look like giant twisted ropes and can occur spontaneously. Their frequency varies according to the 11-year-long solar cycle. For example, at a solar minimum, you can observe one ejection per day, and when the sun is in its most active phase, there might be 3 CMAs per day. Coronal mass ejections disrupt the calm flow of the solar wind and cause serious disturbances that can damage stuff both in space near Earth, like satellites, and on the planet's surface. If coronal mass ejections make it to Earth, their interaction with the magnetosphere generates geomagnetic storms. Those can trigger auroras, happening when a stream of energized particles hits the atmosphere and lights up. And then there are also solar flares. They develop more rapidly and with much more energy than coronal mass ejections. Solar flares often occur soon after coronal mass ejections. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with temperatures reaching several million degrees Fahrenheit. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. A powerful solar storm can potentially cause a devastating global blackout on Earth. If not for the Earth's magnetosphere, the effects of the sun's activity would be much more devastating. Luckily, the magnetosphere deflects most of the solar material hurtling towards our planet from our star at a speed of over 1 million miles per hour. But even so, during space weather events, there's a lot of hazardous radiation near Earth. It can potentially harm astronauts and spacecraft. Plus, space weather can damage large conducting systems, for example, pipelines and power grids, by overloading currents running inside them. Scientists regularly map and track the overall orientation and shape of our planet's magnetic field. To do it, they use local measurements of the field's orientation and magnitude. That's why they've been able to conclude that the location of the North Magnetic Pole has moved by almost 600 miles since the first measurements were taken in 1831. The magnetic field of our planet reverses on a timescale varying between 100,000 to 1 million years. One can tell how often it happens by looking at volcanic rocks at the bottom of the ocean. They capture the orientation and strength of Earth's magnetic field at the time of their creation. So, dating those rocks gives us a good picture of how our planet's magnetic field has evolved over time. From a geological point of view, field reversals happen quite fast, but they are extremely slow from a human perspective. A complete reversal normally takes a couple of thousand years, but during this time, the orientation of the magnetosphere may shift, exposing more of Earth to cosmic radiation. Such events tend to change the concentration of ozone in the atmosphere. In any case, scientists can't say for sure when the next field reversal will happen, but they keep mapping and tracking the movement of our planet's magnetic north. By the way, the Earth isn't the only planet with a magnetic field. Gas giants, like Jupiter, also have a conducting metallic hydrogen layer that generates their magnetic fields. Jupiter's internal magnetic field prevents the solar wind from interacting directly with the planet's atmosphere.
A powerful burst of gamma radiation lasted a mere half-second, but it released an enormous amount of energy. It was more than our sun would produce in 10 billion years. This brief flash lit up the whole sky. Afterward, a much softer and more long-lasting glow replaced it. Astronomers examined the phenomenon with X-ray, radio, optical, and infrared waves. It turned out that people had finally seen a newborn magnetar for the first time ever. It was likely formed after 2 neutron stars had merged. It resulted in a kilonova, one of the brightest and largest stellar blasts. Its light finally reached our planet on May 22, 2020. Imagine a massive star, at least 5 times the mass of our sun, reaching the end of its life. It might be because it's run out of its nuclear fuel. If it happens, the star starts to cool off. The pressure inside drops and the gravity starts to squeeze inward. And then, more than 1,000,000 times the mass of our planet collapses within 15 seconds. It happens so fast that an enormous shock wave causes the outer part of the star to blow up. It produces a blinding burst of light. This powerful blast is called a supernova. What's left behind is an incredibly dense core with a huge cloud of hot gas, called a nebula, expanding around it. If the star has been massive enough, more than 10 times the size of the Sun, it's likely to turn into a black hole. If not, it turns into a neutron star. It's basically a giant nucleus, the central part of an atom. These stars are mostly made up of neutrons and are rarely larger than 20 miles across. For comparison, our Sun is almost 865,000 miles across, which is 109 Earths put side by side. But don't let this relatively tiny size fool you. Any neutron star is at least 1.5 times heavier than our Sun and has an intense magnetic field. If you scooped just a teaspoon of this star's insides, this matter would weigh more than 1 billion tons. It's so dense that it makes neutron stars some of the most extreme objects people know about. The next stop is the black hole itself. When two neutron stars merge, they most often create a new, much heavier one. Within milliseconds, or even less, this star collapses into a black hole. But the astronomers who examined the flash of light recorded in March think there might be another outcome. They're almost sure they saw something never observed before: the birth of a magnetar. That's a rare form of a neutron star with an ultra-strong magnetic field. It's 1,000 trillion times stronger than our planet's. This field is also so powerful, it heats the star's surface up to 18 million degrees Fahrenheit. To put it simply, magnetars are the most powerful magnets in the universe. Their magnetic fields can seriously mess with the neighborhood. Atoms, unlucky enough to get close to such a star, get stretched into pencil-thin lines. If you somehow found yourself several hundred miles away from a magnetar, it would end badly for you. The magnetic field would first disrupt your bioelectricity. It means that your nerve impulses wouldn't work anymore. Even your molecules would change under the influence of the star's field. In the end, you'd pretty much vanish. If a magnetar flew within 100,000 miles from our planet, it would wipe out all the data on every single credit card in the world.
Okay, see that tiny dot in the dark sky? Squint. Still nothing? No wonder. Even though it's very close to Earth in cosmic terms, it's still 18 light-years away from us. But one day, this distant world you can't see with the unaided eye might become a new home to us, because it likely has all the right stuff for life. They're calling it GJ251c, and it's a super-Earth. Now, a quick side note. Super-Earth sounds epic, but it doesn't mean it's some fancy version of Earth with superpowers. It just means it's bigger, somewhere between Earth and the gas giants like Neptune. These planets can be rocky, gassy, like me, or a mix of both. The super only refers to size, not whether you could actually spend your vacay there. Now, this planet sits perfectly in what scientists call the Goldilocks zone. It's not too hot, not too cold, just right for liquid water to hang around. And where there's water, there could be life. We're talking about at least some weird bacteria with serious survival skills. Of course, scientists are still trying to crack the code of what actually makes a planet come alive. There's a whole mix of conditions: distance from the star, atmosphere, and temperature, and GJ251c looks like a top contender. The first thing astronomers check when they stumble across a new super-Earth is if it's rocky like Earth or just another ball of gas like Neptune. Because so far, Earth's still the only rocky world we know that actually supports life. And second, could liquid water exist there? Because water is the ultimate life ingredient. Finding a planet that checks both boxes is super rare. Out of the thousands of exoplanets discovered so far, only a tiny handful hit that sweet spot. So when astronomers realized GJ251c might be one of those, and that is just 18 light-years away, well, they got pretty hyped. The planet star GJ251 is a red dwarf, a small, cool star about 1/3 the size of our Sun. Because red dwarfs don't put out as much heat, their Goldilocks zones are close in, which actually makes planets easier to find. They whip around faster, so scientists can pick up their orbital patterns more easily. Scientists have been keeping an eye on this star for a while, having collected over 2 decades of data. They already knew it hosted one planet, GJ251b, another super-Earth that orbits every 14 days. But sadly, it's way too close to the star to be habitable. But then, digging deeper into the data, the team spotted hints of another world. It was GJ251c. This one looked promising. So astronomers started watching how the star itself wobbled slightly. Those tiny shakes happen when planets tug on their stars with gravity. The bigger the planet, the harder it pulls. Unexpectedly, the researchers didn't just see the signal from the known planet, GJ251b, there was another tug. GJ251c circled its star every 53.6 days. Now, the catch is, we still don't know much about this new world. We got its mass, sure, about 3.8 times heavier than Earth, but since it doesn't cross in front of its star, we can't tell how big it is or what it's made of, yet. Basically, we found its gravitational footprint, but not the planet itself. Still, astronomers are excited. The new world is bright, close, and perfectly placed for future missions to actually see it directly. That's like going from hearing a noise in another room to opening the door and seeing what's making it. Now, at the same time, that kind of direct imaging is incredibly hard. Stars are bright and planets are tiny faint specks right next to them. But the new generation of telescopes, the big ones being built right now, might finally have the tech to pull it off. For now, the team's being cautious. The discovery looks solid, but they want to confirm it with even sharper instruments. The next step might literally be seeing this world with our own eyes, well, through a billion-dollar telescope. But for now, it's a really promising mystery world. It's just a matter of looking closer. But let me tell you another thing, and I bet you didn't expect anything like this. Even if another civilization existed on GJ251c or some super-Earth, they might be totally stuck at home. A new study suggests that for all their fancy tech, they'd have a seriously tough time getting off the ground. And I mean it literally. The problem? Gravity. It's a total spoil sport. The thing is, super-Earths are way bigger and heavier than our planet. As a result, their gravity pulls a lot harder. And when gravity cranks up, so does the fuel bill. It skyrockets, pun intended. Launching a rocket from one of those worlds would take exponentially more fuel than it does here on Earth. On a planet that's about twice Earth's radius, the mass can jump to roughly 10 times that of our home planet. That means gravity could be more than twice as strong as what we feel on Earth. Think weighing 300 pounds instead of 150 just by standing there. Ew. Now, this extra gravity isn't all bad. It helps keep a thicker atmosphere, which means better protection from cosmic rays and radiation. That's great news if you're a microbe trying to evolve without getting zapped every few minutes. The thicker air could also help regulate temperature and even support more complex weather systems. So, for life starting out, that's a big thumbs up. But when it comes to building rockets, it's a total nightmare. That same gravity that holds the atmosphere also chains you down. For example, let's take Kepler-20b, a super-Earth about 1.87 times Earth's radius and 9.7 times its mass. There, a chemical rocket trying to launch just 1 ton, which is about the weight of a small car, would have to be 3 times the size of the Saturn V, and that's the biggest rocket ever built, which carried about 45 tons to the Moon. Even if our hypothetical super-Earth inhabitants were smart enough to dream of space travel, they'd quickly run into a gravity-sized problem. Sure, they might try to build launch pads high up in the mountains to shave off some of the crushing gravity. But on big planets, mountains don't get tall. The immense gravity just squashes them down before they can grow sky-high. Oh, by the way, that's why the tallest peaks in our solar system aren't on the big planets at all. Mars, which is quite a lightweight world, hosts Olympus Mons, a volcano that towers 13.5 miles high. But on a much heavier planet, mountains that tall would collapse under their own bulk before the rocket builders even got halfway up. So our poor super-Earth engineers would probably need to build massive artificial launch towers just to get closer to thinner air. If they had flight technology, like airplanes or helicopters, they might try flying their rockets up first and then lighting the engines in midair. We're actually inching towards something like that on Earth with air-launched rockets. But what if that planet was a water world, and a lot of super-Earths might be? In that case, their smartest species might not even live on land. They easily could be aquatic geniuses. Picture dolphin-like engineers or squid astronomers, forced to launch rockets from underwater. Kind of ballistic missile submarine-type space launches. But even with all that effort, the physics is still tough. For a super-Earth about 10 times Earth's mass, chemical rockets could technically work, but the cost would be ridiculous. You'd need so much fuel that you'd have to burn through a sizable fraction of the planet just to get one ship into orbit. The only real options for super-Earth civilizations might be nuclear-powered rockets or space elevators made of materials stronger than anything we've discovered. Until then, those creatures might stay stuck on the ground with no satellites, no space stations, and no super-Earth NASA. So, as our telescopes keep spotting new, potentially habitable worlds, we probably shouldn't expect to find any weather satellites circling above them. If there's life out there on the super-Earth, it's likely gazing up at the stars, wishing it could visit them, just like we once did. This is a typical crater on the Moon. It's here because, once upon a time, an asteroid crashed right into it. Yep, a lunar crater forms when an asteroid, meteoroid, or a comet slams into the Moon's surface. And as you can see, it's happened a lot. But one crater formed in a very different way. But then, how did it form? Well, let's rewind a bit. There's a widely accepted hypothesis that the Moon itself is a product of collision, just like all these craters. But that collision was way tougher. It happened over 4.5 billion years ago when a huge Mars-sized planet called Theia crashed into Earth. That event threw a bunch of debris into orbit. Eventually, it came together to form the Moon. Now, for a while after that, the Moon was basically a giant ball of lava. But because the early Moon was very close to Earth, our planet's gravity kept squeezing it, making it even hotter. In the end, though, the Moon drifted farther away, cooled down, and formed a rocky crust. Now, moving on, about 4.3 billion years ago, an asteroid the size of a small country, like Nepal, way bigger than the one that wiped out the dinosaurs, slammed into the Moon's far side. It left an enormous crater called the South Pole Aitken Basin. It's up to 5 miles deep and about 1,500 miles wide. For comparison, that's roughly the distance from New York to Dallas and deep enough to swallow Mount Everest. Now, scientists think that impact may have dug up and scattered some ancient stuff from deep inside the Moon, a mixture of materials nicknamed creep, short for potassium, rare earth elements, and phosphorus. It's like a chemical time capsule from when the Moon was still a lava ocean. Now, you want to know the reason why this area could be even more scientifically interesting than we realized? You see, until recently, researchers believed the asteroid came from the south, slamming upward and spreading a bunch of radioactive material, that very creep, around the crater's northern rim. But after looking closer, scientists realized the impact actually came from the north, which means all that valuable creep ended up on the southern edge instead. And guess what? NASA's Artemis 3 mission happens to be targeting that exact southern region. Researchers started questioning the old southern impact theory when they compared the Moon's crater with others across the solar system, mainly Mars's Hellas Basin and Pluto's Sputnik Basin. Here they are. See? All three have this bizarre teardrop or avocado shape, wide on one side and pointy on the other. And exactly that pointy end usually shows which direction the asteroid came from. In the case of the South Pole Aitken Basin, that means the asteroid hit from the north, not from the south. To confirm it, scientists dug into old data from NASA's Lunar Prospector mission. It orbited the Moon in 1998 to 1999. That spacecraft measured radioactive elements on the surface and found high concentrations of thorium, a key part of creep, around the basin's southwestern rim. Now, the Artemis 3 mission is NASA's big plan to put humans back on the Moon for the first time since 1972. If everything goes according to schedule, the launch is set for mid-2027, right after Artemis 2 wraps up. See, Artemis 2, which is supposed to launch before April 2026, will be sort of a dress rehearsal. Astronauts will orbit the Moon without landing just to make sure that all the systems work smoothly, a cosmic test drive. Artemis 3 is where things are going to get real. The astronauts are expected to land near the Moon's south pole, in one of 9 possible locations NASA has scouted out. The only problem is timing. Artemis 3 has already been delayed a few times, and so has Artemis 2. Artemis 1 launched in 2022. It was an uncrewed test flight that went around the Moon and came back just fine. So, next up is Artemis 2, which will take real astronauts further into space. Then comes Artemis 3, the big one. Astronauts are supposed to hang out on the lunar surface for about a week doing sciencey stuff before heading home. After that, Artemis 4 and 5 will build and expand a new mini space station orbiting the Moon. It's called Gateway. Think of it as a pit stop in space. Astronauts can dock there, live for short missions, do experiments, and prepare for landings. NASA's building it with help from the European Space Agency, Japan, and a few others. The astronauts are going to travel in the Orion spacecraft, launched by NASA's Space Launch System, a massive rocket taller than the Statue of Liberty and strong enough to fling people to the Moon. To actually land, they'll use the Human Landing System. SpaceX's Starship is supposed to take the first cruise down to the Moon's surface once it proves it can land safely. In the long run, NASA's not going to stop at the Moon. The big goal is Moon to Mars. Hopefully, we can use everything we learned from Artemis to build a lunar base and eventually send humans all the way to Mars. And who knows? Maybe when people land on the Moon, they'll be able to figure out another unsolved mystery: flickers, glows, or beams of light that sometimes illuminate our satellite. Let's dig deeper into this mystery, shall we? On the night of April 19, 1787, astronomer William Herschel spotted something weird: a bright light glowing on the dark part of the new moon. It shone for hours and was almost as bright as the Orion Nebula. What he saw probably was what scientists now call a transient lunar phenomenon, or TLP. Basically, quick little flashes or color changes on the Moon's surface. TLPs can look like glowing patches, reddish or purple spots, or even hazy clouds that suddenly appear and fade away. Over the last 2,000 years, people have recorded around 3,000 of these strange moon flashes, using telescopes, cameras, or sometimes just their own sharp eyes. So, what's really going on up there? Well, there's no single answer. Lots of different things can cause TLPs, from meteor impacts to gas releases or even electrical activity. The length of the flash, which can last anywhere from a split second to several hours, gives scientists clues about what's behind each mysterious lunar light show. The super short flashes lasting less than a minute are most likely caused by tiny space rocks crashing into the Moon. Even a meteoroid, the weight of a billiard ball, can hit the lunar surface hard enough to make it glow for a split second. The heat from the impact makes rocks shine and then quickly fade as they cool down. For a long time, scientists suspected these quick flashes were caused by meteor hits, but they couldn't prove it until the 1990s, when high-speed cameras finally became common in lunar research. Even then, it wasn't easy to confirm. Short flashes could have just been camera glitches or electric noise. The only way to be sure was to catch the same flash from 2 or more places at once. Well, that happened for the first time during the Leonid meteor shower in 1999, when scientists recorded real impact flashes on the Moon. Later, we got more proof that the Moon was often peppered with space rocks. While the flashes seemed to cluster in certain areas, like Oceanus Procellarum, one of the Moon's big dark plains, that's likely just because of where scientists have focused their cameras. A 2024 study showed that meteoroids actually hit the Moon evenly everywhere. Now, flashes that last a few minutes are probably caused by something totally different – gas leaks from inside the Moon itself. Studies from 2008 and 2009 found that when gas like radon builds up under the lunar surface, it can suddenly burst out. Hey, I know how that feels. And when this radioactive gas escapes and decays, it gives off a faint glow we can see from Earth. Interestingly, those glowing spots often line up with areas where scientists have already found higher radon levels. Then, there are the long-haul lights. They stick around for hours, like the bright glow William Herschel saw back in 1787. A 2012 study suggested those could actually be caused by solar wind, a stream of charged particles coming from the sun. When that solar wind hits lunar dust, it can charge up the particles and toss them into the air, well, into space, creating massive dust clouds up to 60 miles high. These floating clouds might bend or reflect light from stars or planets nearby, making it look like the Moon itself is glowing. So hopefully, we'll get the answers once the Artemis mission lands and starts its exploration. Hey, I can hardly wait.
Remember that asteroid that wiped dinosaurs off the face of the Earth? Brace yourself, we might witness a similar scenario in our lifetimes. And this time, the consequences might even be more catastrophic. There's just one tiny difference. This new asteroid is likely to smack into the Moon. No, this is not a sci-fi scenario anymore. There's this asteroid called 2024 YR4 that scientists say has about a 4% chance of hitting the Moon in 2032. So what do? Try to gently shove it off course or blow it up? A bunch of researchers, including people from NASA, dug into this and suggested several options. Their worry is real. If that rock hits the Moon, it could kick up a massive cloud of debris, and this cloud could spike to as much as 1,000 times normal levels for a few days. That's not just messy, it could endanger astronauts and satellites in low Earth orbit. One obvious idea is to nudge the asteroid so it misses the Moon. Another is a full-on breakup. Basically, a deliberate explosion. Experts use a clever term to describe it, a robust disruption. But nuking an asteroid is totally untested. Nobody has ever done it before, and it carries huge risks. You could create a bunch of smaller but more dangerous fragments, or do something unexpected that can make things worse. In any case, the idea is out there for scientists to chew on. Now here's the backstory. 2024 YR4 was first spotted on December 27, 2024, and reported to the Minor Planet Center. That's the official hub that tracks all new asteroids and comets. Pretty soon, it showed up on NASA's Century Impact Risk Table, which is like the agency's watch list for any asteroid that could potentially hit Earth. For a little while, things looked sketchy. Out of 37,000 plus known large asteroids, YR4 was the only one with a real chance of smacking into Earth anytime soon. Its odds even climbed to a record 3.1%.
That might not sound like much to such amateurs as me and you, but in space terms, that's huge. Scientists were really paying attention. Luckily, after a few more months of better tracking and sharper observations, they nailed down the asteroid's orbit more precisely. Turns out its path isn't taking it anywhere near us after all. Its chance of hitting Earth has dropped so low it's basically zero now. So, we can breathe out and relax. Earth is safe. But the moon? Maybe not. And that's why researchers are now debating whether to blow the thing up before it ever gets close. The thing is, asteroid 2024 YR4 is pretty big. Based on what the James Webb Space Telescope saw, it's about 220 feet long, roughly the size of a 20-story building. Not exactly a pebble, I'd say. At first, NASA thought there was only around a 1.7% chance that YR4 would crash into the moon. But then, the Webb telescope checked again in March, and that number jumped to 3.8% right away. By May, it climbed once again. It was already sitting at about 4.3%. In other words, the more they looked, the more likely it seemed that this space rock might actually hit our natural satellite. On the bright side, these new observations helped NASA figure out where exactly the asteroid would be on December 22, 2032, with about 20% better accuracy. Now, if the asteroid really did smash into the moon, NASA says it wouldn't mess with its orbit or make it wobble or anything dramatic like that. And this is a very big but a hit from something that large would kick up a ton of debris, and that flying space junk could become a real problem for satellites orbiting Earth, or even for astronauts on the International Space Station. That sounds alarming enough. That's why the story might take a turn straight out of a sci-fi movie. Scientists are seriously considering blowing the asteroid up. But unlike in a movie, this isn't about saving Earth this time. The most extreme idea is to launch a bunch of nuclear explosives at the asteroid before it reaches the moon. The thinking is, if they can blow it to pieces while it's still far away, the debris will scatter safely into space instead of causing problems near Earth. But of course, there's the catch. While scientists know roughly how big YR4 is, they don't know exactly how much it weighs. And that's a huge problem. Without knowing its mass, space agencies can't design a precise mission to knock it off course. In theory, they could send out a reconnaissance spacecraft first, something to get close to the asteroid, measure it up, and figure out the best way to push it away. But researchers say there just isn't enough time. By the time we'd collect all the needed data and build the right hardware, it'd be too late to intercept the asteroid before the 2032 impact window. So instead of a gentle space nudge, some experts suggest going full Armageddon-style, that very robust disruption. Translated into human, it's blasting the asteroid apart with nuclear explosions. Sure enough, this idea comes with a massive risk. What if the explosion accidentally changes the asteroid's path and sends some fragments toward Earth? The researchers admit it's a possibility, but still think nuking it could be the most practical solution, given the circumstances. If the mission ever happens, it would need to launch sometime between 2029 and late 2031. This would give it just enough time to reach and intercept the asteroid before it gets too close to the moon. Now, nuking space rocks might sound over the top, but NASA actually has some experience with asteroid defense. Back in 2022, they pulled off something groundbreaking with their Double Asteroid Redirection Test, or DART. That mission was all about proving that humans could physically change an asteroid's path without using explosives. NASA launched a small spacecraft in November 2021, and after almost a year of travel, it crashed head-on into a tiny asteroid named Dimorphos at about 14,000 miles per hour. The idea was simple. If you hit an asteroid hard enough, you can slightly change its orbit, just enough to make it miss Earth someday. And it actually worked. The test showed that even a relatively small spacecraft could make a serious difference. Now, the European Space Agency wants to double-check exactly how much of an effect that crash had. In October 2024, they launched a follow-up spacecraft called Hera from Florida's Cape Canaveral Space Force Station. Hera's on a 2-year journey to reach Dimorphos and its bigger partner asteroid, Didymos. By October 2026, Hera will enter orbit around the asteroid pair and start collecting data, basically checking NASA's math. ESA scientists hope that once they analyze the impact site, they'll find out how effective DART was at changing the asteroid's trajectory. If it turns out that kinetic impact, aka smashing a spacecraft into an asteroid, works well enough, future missions might use that technique again. Maybe even for YR4, if it ever becomes a real threat. But if it doesn't, that's when the nuclear backup plan might come off the shelf. Either way, scientists are making sure that if a space rock ever threatens Earth or the Moon, humanity will have more than just a Hollywood script to rely on. By the way, people at NASA run what-if asteroid exercises every 2 years to get scientists, state agencies, and international experts on the same page. During such asteroid drills, experts pretend that a giant space rock is heading our way. Then they work through all the tricky questions they can come up with, like how big is it, where might it hit, what should we do? It's like a massive brainstorming session to make sure that if this ever happens, we won't be starting from scratch. To make these scenarios feel as real as possible, NASA's Center for Near-Earth Object Studies gets involved. These are the folks who track real asteroids and calculate their orbits. So they simulate months of asteroid observations, complete with uncertainties about its size, trajectory, and potential impact zones. No one knows exactly how big the asteroid is or where it can hit. It's the kind of uncertainty that makes decision-making way harder, just like it would be in real life.